Okay, so last time we discussed oscillations and now we will continue this topic, and the next issue we will consider will be damped oscillations. Damped. Damped oscillations. Well, you remember when I demonstrated oscillatory motion like that of a mathematical pendulum or spring pendulum when a body was oscillating on a spring. You remember that these oscillations did not continue forever. They faded and they decayed. The amplitude was diminishing with time, and finally the oscillations totally ceased. Such oscillations with decreasing amplitude are called damped oscillations, and we will consider this topic and how can damped oscillations be described theoretically. So if there is a body on the spring, a body of mass m, which can slide on horizontal surface along the x-axis, and the spring of stiffness k attached to a wall. So this body may oscillate, and let this be a point of equilibrium, and this is the current coordinate of the body, and all the physical quantities directed to the right will be considered as positive, and all the quantities like velocities and displacements and accelerations directed to the left will be considered as negative. So we have already written an equation which describes such motion. This is second Newton's law. Second Newton's law. Acceleration is certainly second derivative of the coordinate x. So mass times acceleration is the total force acting on the body, and the total force in our previous considerations was the force acting on the body from the spring, and that was minus kx. Why minus? Because if x is positive, then the spring is extended and it's exerting a force directed in the negative, in the opposite direction, opposite to the displacement x. That's why if x is positive, then the force will be negative, directed oppositely, and vice versa. If x is negative, that is, the spring is compressed, then the force from the spring, acting from the spring on the body, will be directed in the positive x. So if x is negative, the force will be positive. If the oscillation is damped, then the amplitude of oscillation is decreasing with time, and this is caused by forces of friction or forces of air drag, and we will consider viscous friction only. We will not consider dry friction. Dry friction is more complicated thing. We will start from viscous friction or air drag, and the forces of air drag should be added here to the force from the spring. There is another force acting from this viscous friction, and that will be proportional to the velocity of the body. Velocity is the first derivative, x dot, and mu is the coefficient of proportionality between the velocity and the force of air drag or viscous friction. And again, if the velocity is positive, that is directed to the right, then the force of air drag will be directed to the left. That is why we will have minus sign here. Again, all the quantities directed to the right will be positive, and all the quantities directed to the left will be negative. So that is the force of air drag. What is important is that this force is proportional to the velocity of the body. Experiments show that this is true for small velocities. not very high velocities. If the velocity is growing, if it's large enough, then the force will be proportional to the square of the velocity. But we will not consider large velocities, we will consider small velocities when this body just is oscillating here, the velocity is not very large. So in our case, when the velocity is not very large, the air drag force is proportional to the first degree of velocity, the first order. And so we don't consider large velocities when the air drag is proportional to the second degree, x dot squared. We don't consider such high velocities. Okay, we will take all these terms to the left-hand side, and we obtain mx 2 dots plus mu x dot plus kx. X is a function of time, certainly, because this is a current coordinate, and all this is equal to 0. And as we did before, we will divide this equation by m, by the first coefficient, so that the highest derivative will have no coefficient, or it's better to say will have coefficient 1, unit coefficient. So we will obtain x 2 dots plus mu divided by m x dot plus k divided by m x equals 0. When we considered oscillatory motion without friction, we had this second term here, and you remember that this coefficient was equal to the frequency of oscillations squared. This coefficient is usually denoted as 2 beta. Y2 is introduced here for simple purpose so that this coefficient will not appear in other important places. Let it be here 2 beta so that it's eliminated from other places. So finally we obtain this equation, x 2 dots plus 2 beta x dot plus omega 0 squared x equals 0. And we have to find this unknown function x as a function of time. X as a function of time, which is unknown, and we need to find it. There are certain methods to solve these differential equations, mathematical methods. I will not waste my time on maths. I will simply give you the final answer. And what is clear from the very beginning is that we have the second order differential equation because there is a second derivative. And if you have second order differential equations, then the unknown function will contain 2 unknown constants. So we may define the solution to this equation up to the 2 unknown constants. And the 2 unknown constants shall be defined from initial conditions in each particular case. When you solve any particular problem, you have some initial conditions, initial displacements, initial velocities, and these initial conditions will allow you to define 2 unknown constants, 2 undefined constants, which will be here. And the solution to this equation will be this. It will be some constant, which is initial amplitude, exponent to the power minus beta t cosine omega t. Such function is the solution to this equation under simple condition, under the condition that omega equals square root of omega 0 squared minus beta squared. If omega, the oscillation frequency, is related in this way to omega 0. And you know what is omega 0? This is square root of k divided by m. Stiffness of the spring divided by the mass of oscillating body. This is omega 0. And beta is the coefficient proportional to air drag. Then the body will oscillate with some frequency which differs from its own frequency, omega 0. The own frequency will be found when there is no friction, no air drag, when beta is 0. Then the oscillation frequency will coincide with the own frequency of the body. But if there is some friction, then the oscillation frequency will become a little bit smaller than the own frequency, omega 0, because of the friction. So this beta, which was introduced here as the coefficient of friction, appears here as the argument, as part of the argument of the exponent. And what is the dimension of this quantity? The argument of the exponent should be dimensionless. This should be a dimensionless number. Therefore, beta should have units equal to seconds, 1 divided by seconds, in order to compensate seconds, units of measurement of time. So beta must be equal to 1 divided by some time period. Beta is constant, characterizing the air drag, and time period tau is also some constant. And if we use this new quantity tau, which we introduced based on the units of measurement of beta, the units of measurement should be seconds to the minus 1. That should be seconds to the minus 1, total units of measurement. So based on this units of measurement, we introduce a new quantity tau. And now the physical sense of beta is clear. If beta equals 1 over tau, then this equation, then this solution becomes initial amplitude A0 E exponent of minus t divided by tau cosine omega t. Now it's absolutely clear what is the physical meaning of tau. Tau is such a time interval during which the amplitude will be reduced by a factor of e. So if time equals tau, then the amplitude of t will be equal to the initial amplitude exponent to the power of minus 1, if t equals tau. So tau is such a time interval during which the amplitude decreases by a factor of e. And e is the well-known constant. It's approximately equal to 2718261, etc. Something like this. E is a very special constant. Why this constant is important in mathematics? I told you already that if you consider function f of x equal to exponent to the power of x, then df dx will be equal f of x. That is the only function whose derivative coincides with the function itself. The only function possessing such quality is the exponent e to the power of x, where e is such a constant. Why this constant is important? It comes from this condition, originates from here. So this exponent, such an exponent plays very important role in physics, and both in physics and in mathematics. And here we have it in this solution. So what is beta now? We know the physical sense of the beta. This coefficient is a reciprocal, it's the reverse time interval during which the amplitude is reduced by a factor of e, where e is such a constant. Can we draw a graph of such function? Certainly, it's not a complicated task. So here we will have x of t shown along vertical axis, and here we will have time, and the initial amplitude a0 will be here. A0 at the initial moment of time t equals 0, and exponent will be 1, cosine of 0 also 1. So the graph of this function starts from point A0, and then it goes oscillating as dictated by cosine, by this harmonic function, but the amplitude of oscillations is decreasing with time. So the oscillations will go with decreasing amplitude, something like that. The amplitude of oscillation as a function of time will be equal to A0 e minus beta t. The amplitude of oscillations will be decreasing with time. And this quantity omega will define the period of oscillations. Here we can indicate the period of oscillations. This time interval will be a period of oscillations, which is 2 pi divided by omega. This omega, which depends both on the spring stiffness and the air drag coefficient. Suppose the air drag is growing and beta becomes larger and larger. Then the oscillation decay time will become smaller and smaller, and the amplitude will decrease quicker. And if beta grows and becomes equal to omega 0, then that will become 0. What does it mean, zero frequency? It means that there are no oscillations at all. In this case, this function will turn into something like this, the initial amplitude, and then no oscillations, but just decaying position. That is the position which is along vertical axis will tend to 0. Such a motion is observed when the medium is very viscous, like the body, this body on the spring moves in a very viscous liquid like honey, for example, very viscous. If you make an initial displacement of this body, then the spring will remove it to its initial position slowly. There will be no oscillations if the environment is very viscous. And that will be the situation, such situation when beta is equal to omega 0, or even larger than omega 0. If it's larger, then again, no oscillations at all, but just a graduate return to initial position. That was the initial position, the position of equilibrium when coordinate was 0. So such a motion without any oscillations occurs when you have a very viscous medium with a very high viscosity and a high drag, high friction, viscous friction. Another thing I would like to discuss is a phase portrait. Phase portrait of damped oscillations. Sometimes it's very useful to depict oscillations using a different way of presentation, not the coordinate as a function of time, but a different way to present the motion. And this different way consists in drawing a picture of the velocity of oscillating body x dot as a function of x, as a function of its coordinate. Such a graph in such axis is called phase portrait. It's a phase portrait. Let's try to show the motion of oscillating body on a phase portrait. So let it be the initial amplitude, the initial position of oscillating body. It's displaced from 0. If we let this body move, the spring will try to return the body to the initial position of equilibrium. And the velocity, the body will move to the initial position, but the velocity will become negative because the initial position was positive. The velocity will become negative. It means that the initial position will become smaller and smaller, and the velocity will become larger and larger, but negative. And in this point, the initial position the body will be in its equilibrium position, but the velocity will be large negative. And the body will continue moving, and the position will become negative, and the velocity will become 0. And then the body will continue moving in positive direction of displacement, and the velocity will become also positive. And then the body will return to this point, and that will be undamped oscillations. Undamped oscillations will have such a phase portrait. Undamped oscillations. Undamped oscillations. If the oscillations are damped, then the velocity will not be as high because some of the kinetic energy, some of the mechanical energy will be lost on the work performed against the forces of friction, and so the velocity will be smaller, the magnitude of velocity will be smaller, and the body will move along different trajectory, and the amplitude, negative amplitude, will be not as large as it was in the case considered above. It will not be minus A0, it will be smaller, and so the damped oscillations will be presented by such a spiral, when the amplitude decreases with time and the velocities decrease, and finally this spiral goes into 0 point. So such will be the phase portrait of damped oscillations. Damped oscillations. Phase portrait is very useful in solving different complicated problems, including parametric resonance, including many other problems related to oscillatory motion. Phase portraits are widely used in physics, in scientific investigations. Next, I will consider some quantities very important in describing the damped oscillations. The first quantity will be logarithmic decrement. Logarithmic decrement. By definition, logarithmic decrement is a natural logarithm of the amplitude at time moment t divided by the amplitude of oscillations at time moment t plus capital T plus period. What is period? We have already discussed. So this is the definition of logarithmic decrement. This quantity is called a logarithmic decrement of damped oscillations. That is a natural logarithm of the ratio of two amplitudes. The ratio of two amplitudes which are separated in time by a period of oscillations. The next amplitude is smaller than the previous one because the oscillations are damped. So the denominator is smaller than the nominator, and so that this ratio is larger than unit. And what is logarithm? Natural logarithm, do you know? So if you have a equal to e to the power of b, then natural logarithm of a will be b. By definition of this function, logarithm. Okay, what is the amplitude in damped oscillations? We have already discussed this issue. That is the amplitude, and we can use this function here. That will be logarithm a0 e to the power of minus beta t divided by a0 e to the power of minus beta t plus capital T plus period. Almost everything will be cancelled here. A0 cancels, and what remains is logarithm of 1 divided by minus beta capital T, 1 divided by e to the power minus beta capital T. And that will be a logarithm of exponent, or simply beta t. And we know what is beta. Beta is 1 over tau. By the way, tau is called a relaxation time or relaxation constant of damped oscillations. So tau has the name. This quantity has the name. It's a relaxation constant or relaxation time. Relaxation time of the damped oscillations. So beta equals 1 divided by tau, and here we will have period divided by tau. What if we consider tau divided by period? Tau is the time needed to reduce the amplitude by a factor of e. And if we divide this time period by capital T, we will obtain the number of periods in this time interval. That will be the number of periods such that the first amplitude of the first oscillation is by a factor of e larger than the last oscillation. That is the number of oscillations such that the amplitude of the first oscillation differs by a factor of e from the amplitude of the last oscillation. So tau divided by t has clear physical meaning, and here we have t divided by tau, so that will be 1 divided by n. That is the logarithmic, the meaning of logarithmic decrement. The meaning of logarithmic decrement. Another important quantity which is used to characterize damped oscillations is a quality of oscillator quality, or quality factor, or Q factor, quality of oscillator. By definition, it's defined as 2 pi energy of oscillation at time moment t divided by the energy loss during one period of oscillations. By definition, this is not a consequence of some physics law. This is just the definition of physical quantity. By definition, why 2 pi here? Why do we have 2 pi? We introduced 2 pi coefficient here in order to eliminate it in other places. That's it. So we divide this ratio by E and obtain 1 minus energy at time interval t plus capital T divided by E in time interval, in time moment t. So this is the ratio of energies accumulated by an oscillating system in 2 time moments separated by period. What is the energy? We discussed it. Energy in oscillations, in oscillatory motion, the energy is proportional to amplitude squared. So if the energy of oscillations at any time moment is proportional to amplitude squared, and the amplitude is known to us, amplitude is here, then we can use this knowledge to modify this function. So this energy is proportional to the amplitude squared. I have to take amplitude squared. Certainly A0 squared will cancel in this ratio. A0 squared will be both in numerator and in denominator, and I will have to take into account only exponential factors. So exponent minus 2 beta t divided by exponent minus 2 beta t plus, oh, it's different, t plus capital T, and here is simply t. And what remains here will be 1 minus exponent y2, because the energy is proportional to the square of the amplitude, and when we take the square of this function, we will obtain a factor of 2 here before beta, at the beta. So exponent minus 2 beta will be cancelled here, and what remains, exponent minus 2 beta capital T period of oscillations. Approximately, this is approximately what? What is beta capital T? We have already encountered this quantity here when we considered a logarithmic decrement, and we know that this quantity equals to 1 divided by the number of oscillations during which the amplitude decreases by a factor of E. If oscillations are slightly dampened, that is, the damping coefficient is small, beta is small, then this number of oscillations will be very high. The system will oscillate and oscillate thousands of times before the amplitude decreases by a factor of E. So this is very small quantity if the damping coefficient is small. If friction is small, then this is the number n will be very large. and this quantity beta tau, beta t will be very small. If this is very small, then we can use the expansion of the exponent. The exponential function can be expanded into a Taylor series like 1 minus 2 beta t plus, and I will neglect all the other factors here. I'm using this formula that e to the power of x approximately equals 1 plus x squared divided by 2 plus etc. etc. All the remaining higher order terms will be neglected if x can be neglected if x is very small. If x is very small, I can take only the first two terms in this expansion. Have you already studied Taylor's expansions? Okay, so you know this formula, right? Okay, good. So I take only the first term here in this expansion because x is very small. Why it's very small? Because of physics conditions, because we consider a very slow damping process. So if this is very small, then we open this round brackets, and 1 minus 1 will give us 0, minus by minus will give us plus, and we obtain 2 pi divided by 2 beta t, which will be pi divided by beta period. That is the quality factor of a decaying oscillator. It can somehow be, it can be presented in many different forms. For example, what is beta t, beta period? We know this is by definition is a logarithmic decrement d. So what is in denominator here is just a logarithmic decrement d. That's a very useful presentation of Q factor of tempered oscillations. It's just pi divided by logarithmic decrement. And logarithmic decrement was found to be 1 divided by n. So this can be continued and presented in the form as pi n, where n is the number of oscillations during which the amplitude decreases by a factor of e. So it may be thousands of oscillations multiplied by pi. So the quality factor of slowly of oscillatory system with small damping factor, the Q factor may be very, very large, more than 1,000, more than 10,000. And if you consider mechanical oscillatory systems, then this Q factor may be of the order of 10,000 or more. But if you consider electrical circuits with oscillations in electrical circuits, then the quality factor may be even high. It may be millions and millions. And quality factor describes the speed of decay. No, it describes in a way, it describes the this constant tau, which is a relaxation time. It's related to relaxation time because it's related to beta. And from different point of view, we may consider relaxation constant tau, or we may consider quality factor, or we may consider a logarithmic decrement. All these are different ways to characterize the tempered oscillation process. So we have 5 minutes interval, 5-minute interval. Okay, we continue after a short interval. So looking at this formula, I would like to remind you what is this period, the period of oscillations. Period of oscillations is related to frequency of oscillations by a formula 2 pi divided by frequency. And if the damping coefficient is very small, where is that formula? I have already wiped it out. So if the damping coefficient is small, then the oscillation frequency, which is equal to omega squared minus beta squared, if beta squared is very small as compared to omega 0, then this is very close to omega. The oscillation frequency will be very close to omega, which is defined for a spring pendulum as k divided by m square root. That is in case, that is if beta is much smaller than omega 0. If the second term here is much smaller than the first term, then approximately this will be correct. So in this case, the period, the oscillation period will be equal to 2 pi divided by omega 0. Omega 0 is very close to omega. And here I will use this formula and write it down as pi divided by beta. And instead of oscillation period, I will use this formula. I will write 2 pi divided by omega 0. So omega 0 will go to the denominator and pi will cancel, and I will obtain omega 0 divided by 2 beta. This is another way to present the Q factor, the quality factor. And now I will need more space, probably here. Is it possible to show this part of the blackboard? Okay. Let's consider the energy of oscillations as a function of time. The energy is proportional to the amplitude squared. And the amplitude is given by this formula or by this formula. It doesn't matter, it's all the same. So the amplitude squared will be A0 squared E minus 2 beta t. That will be the dependence of energy of oscillator versus time. And now I will use beta expressed from this formula. So from here we can write that beta equals omega 0 divided by 2 Q factor, by 2 quality factor. So instead of beta, I will use this expression using the quality factor, and that will give me what is A0 squared. That is the initial energy at the very start of oscillations when time is 0. When time is 0, the exponent will be unit, and the initial energy at the initial time will be A0 squared. That's the initial energy of oscillations, and here I will get minus 2 beta, but beta is omega divided by 2q. So I will have omega 0 time divided by q. 2 will cancel. This quantity omega 0 time is sometimes denoted by theta and called dimensionless time. Dimensionless time. So this is time when we multiply it by omega 0. That is dimensionless quantity, and which is proportional to time. It's called dimensionless time. The physical meaning of this dimensionless time is obvious. It's the number of radians covered by the oscillating system. Okay, in this case it will be E0 exponent minus dimensionless time theta divided by quality factor Q. And here is another physical meaning for a Q factor. A Q factor, according to this formula, the meaning is obvious. The Q factor is the relaxation constant for the dimensionless time. Is the relaxation constant for the dimensionless time theta. Relaxation. So the quality factor may be expressed in different ways, and it has many important physical meanings. For example, it's pi divided by logarithmic decrement, and it's also pi multiplied by the number of oscillations which are important, during which the amplitude is reduced by a factor of E. And also the quality factor is the relaxation constant for the dimensionless time. And there will be many more physical meanings for a quality factor. Now I will consider another important topic. So we have finished with damped oscillations, and we will consider another important topic, which will be forced oscillations. Forced oscillations. This term, forced oscillations, means that the oscillations do not go by themselves, but are somehow forced by external agent, by external forces. Something from some external force acts on the oscillating system. Some external force acts on the oscillating system. And what happens if the external force is acting? So far we have considered the oscillation equation in this form: x2 dots, which is acceleration, plus 2 beta x dot, which is the force of viscous friction, plus omega 0 squared x. And that was equal to 0. Now we add another external force, and we will consider a harmonic force which is acting on the oscillating system not constantly but periodically, harmonically. Harmonic force will be, harmonic force is proportional to cosine omega t, for example. So that will be, harmonic force will be amplitude, magnitude of the force, and as this equation was divided by m, so that will be divided by m cosine, and we already had several different omegas. We had omega 0, which is the own frequency of oscillating pendulum, and I will write it for the example. I will write it. Sorry. Someone has this. No, it's not mine. Can we somehow see it too? Oh, it's mine, yes. I'm sorry, I've forgotten to switch it off. And I've forgotten that I have taken it with me. Okay, so on the example of a spring pendulum, this own frequency is related to the stiffness of the spring and the mass of oscillating body. For different oscillating systems, the formula will be different, but I will stick to this example because The generalization is obvious for any particular case. This frequency will be defined by different formulas in different particular problems. But for the spring pendulum, it will be defined by the spring stiffness K. So we had omega 0 and we had omega for a decaying, for a dampened oscillations, which is omega 0 squared minus beta squared. And now we must have some different omega, which does not coincide with these two omegas. So I will denote this different omega by capital letter omega, capital Greek letter omega. This is the frequency of external force acting on oscillating body. The frequency of external force, it should not necessarily coincide with these frequencies which we have already considered. It's a different frequency. It may be any frequency, because an external force may push the oscillating body at any frequency. I define this frequency by myself. I can choose any frequency of external force because I define the external force by myself. I can be the external force. I can exert this force. So I can push the oscillating body with any frequency which I choose. So this is any frequency, and we have to find the solution to this differential equation, which describes the oscillations under the driving force, that is external force that drives the oscillations. So if we act on this vibrating system, you may imagine the body on the spring, and if I shake this body with some frequency, it will be moving with this frequency which I define. So the body will move at the same frequency of the external force. But what is most interesting, what will be the amplitude of such motion? And what will be the phase of such motion? Because the phase may not coincide with the phase of external force. And the amplitude will depend on the omega, on the frequency of external force. So we have to find the solution, and from physical consideration, from intuition, we may be sure that the solution has this form. It will have some amplitude, amplitude of oscillations for the coordinate of oscillating system. Amplitude will depend on the frequency of external force, and then there will be cosine, and the body will oscillate with this frequency, capital omega, and also the oscillations will either lag behind or will have some additional phase, which will also depend on this frequency, which will also be a function of capital omega. So that must be the general expression for the solution. You may take this function and substitute it here for x, and you may take a derivative of this function with respect to time and substitute the derivative for x dot, and you may take the second derivative of this function and substitute it for x 2 dots, and you may consider this solution mathematically, and you will finally obtain the expression for this very interesting function. The most interesting function is the amplitude as a function of the frequency of the external force. That is the most interesting thing. You can obtain it by just differentiating this function and substituting here in the equation and solving this equation. But this is a lengthy mathematical calculations, and I will show you the way. I will show you the method which immediately gives the result, if only you know what is an imaginary number, a complex number. Do you know what is complex numbers? Okay, so I will just remind you that a complex number is x plus imaginary unit like y, where x is called the real part of complex number and y is called an imaginary part of complex number, and I is just the square root of -1. Right? You know this? So a complex number can be presented on a plane, which if we choose xy plane, and this will be not merely y, but imaginary axis, so that instead of unit we have imaginary unit I here, and then any complex number x plus I y may be presented as a dot on such a plane, so that this will be its x coordinate and that will be its y coordinate, and also there will be some phase of this complex number. Any complex number may be presented in the form of amplitude of complex number, which is just the length of this section, that is the amplitude, times exponent I phi, which is the angle or argument, the angle at which we see this complex number on the plane, or the argument of complex number. You know these things, I'm just reminding you. And there is a beautiful formula of Leonhard Euler. Leonhard Euler proved that exponent of I phi equals cosine phi plus I sine phi. This is a beautiful and very interesting formula of Leonhard Euler. Leonhard Euler, an Austrian mathematician who most of his life lived and worked in Russia, in Petersburg. So, if you remember how this formula is proved, by the way, it's very simple. You have to consider the Taylor series expansion of exponent, and if you use the Taylor series expansion, you will see that the Taylor series for this function coincides with the sum of two Taylor series for cosine plus I sine. That is proven when you consider, can easily be proven when you consider the Taylor expansion for all these functions. So, based on the knowledge of complex numbers and based on the understanding that the solution of this equation will be harmonic function, some harmonic function, we will use a complex function, exponent, complex exponent, because here we have cosine, and here also we have cosine. And we understand that if we change the initial phase, what is the initial phase? It's just the moment of time when we start the clock. We may start the clock at any moment of time. If we shift this initial moment of time, then cosine will turn into sine, or cosine will turn into any harmonic function with an arbitrary additional phase depending on the initial moment of time, on the choice of initial moment of time. So cosine and sine are actually the same function, differing only, depending only on the initial moment of time, when we start the clock. So cosine and sine are functions, well, identical, practically very similar functions. And here this complex exponent incorporates both cosine and sine, and cosine incorporates both harmonic functions, and harmonic function is what we need here. So we use this mathematical trick, and we will look for the solution in the form of A, which must be a function of the driving force frequency and exponent of capital omega t. exponent of I capital omega t. That is the form of solution which we will try to find. We will try to find the solution to this differential equation in this form, because we are sure that the body coordinate x of t will change in time with frequency capital omega, the frequency of external force. And the equation itself will also, the cosine omega here will also be substituted by the exponent, so that the equation will become this one: x2 dots plus 2 beta x dot plus omega 0 squared x equals f0 divided by m exponent I omega t. So this complex exponent will be used also to denote the external force, the driving force, which drives the oscillations, and it will be used to find the solution to this equation. So if we differentiate this function, we will obtain a, and when we differentiate with respect to time, we will have here I omega exponent I capital omega t. And the second derivative will be a, and again, differentiating this function, I will obtain I omega squared exponent I capital omega t. And then substituting all these expressions into this equation, I will obtain the following: x2 dots. First of all, we note that each term in this equation, each three terms in the left-hand side of this equation will have a, the amplitude, as a factor. So I can immediately factor a, and then I will have inside the brackets what remains after I substitute for x2 dots this expression. I squared will give me minus omega squared, and also this exponent will be a factor in each term here and also a factor in the right hand side, and it will be cancelled. The exponents will cancel, and what remains of the second derivative minus omega capital squared. Of the first derivative, I will have plus 2 beta, the coefficient here, x dot, and x dot is proportional to I capital omega, and plus, when I substitute this expression for x, I will obtain just omega squared, 0 squared. And all this is f0 divided by m. Exponents cancelled. All the complex exponents cancelled because they are present in each term of this equation. And also the amplitude a can be factored here in the left-hand side of this equation, and that's what we obtain after substituting this function into the equation. So we have the differential equation, which is based on the second Newton's law, describing the motion of our oscillatory system. The second Newton's law, and based on physical understanding of what's going on, I'm looking for a solution in this form. I'm looking for a solution for an unknown function. I'm trying to find the unknown function x of t in this form, and substituting this function into the equation together with its first derivative and second derivative, I arrive to this equation. So I can immediately find this function a, amplitude, as a function of the driving force frequency, which will be f0 divided by m, and also all this divided by what we have here, omega 0 squared minus capital omega squared plus 2I beta omega. That's the complex amplitude. So what does this result mean? This result means that the function we were trying to use as the solution to this equation can sometimes be actually a solution, but not always. This function is not always a solution. It will be a solution if this coefficient A is defined by this formula, because we have found this formula from demanding that this will be a solution to the equation, to differential equation. So on condition the amplitude of oscillation is defined by such a complex function. On this condition, this function will actually be a solution to this equation. So how now to find actual amplitude? If we have a complex number, this is a complex number. This is a complex number because we have here a complex unit. So if we have an arbitrary complex number and its argument is changing in time in this way, changing in time, and the complex exponent is defined as cosine phi plus sine phi. That will be cosine omega t plus sine omega t. What does it mean if x is proportional to cosine omega t and y is proportional to sine omega t? It means that this point is rotating at some frequency omega, going along the circular trajectory on this complex plane. So if it's rotating, then its coordinate will be changing, its x-coordinate will change. And what will be the amplitude of this change? The amplitude will coincide with the amplitude of complex number. And in order to find the amplitude of complex number, the amplitude A of complex number, I will put it in this way, the amplitude of z, it will be square root of x squared plus y squared. That is the real part of the complex number squared plus imaginary part of the complex number squared. So in order to find the amplitude of oscillations, real oscillations, I must find the amplitude of the complex number. So the logic was this. Originally, I understand that the external force depends on time as cosine. But instead of cosine, I use the complex exponent, keeping in mind that this is just a mathematical trick. And final answer will be just the real part of this mathematical function, just the real part which is cosine. So I will have to find the amplitude of the real part, the amplitude of this function. That will be the amplitude will be given as the square root of the real part and the imaginary part, because this is the amplitude of the complex number which in time will describe the circle, and so that the real part of this complex number will be varying as cosine, as harmonic function in time, and its amplitude of its oscillation will coincide with the amplitude of the complex number. So I must have just to find the amplitude or the modulus of this A. So this is the real number. I don't have to change it. It's a real number, and I have to find the denominator is the real number, and I have to find the amplitude of the complex number which is in denominator. And I have to use the Pythagorean theorem, this one, that is, I have to take the square of the real part of the complex number plus imaginary part squared of the same complex number. So what is the real part here? That will be squared. That will be omega 0 squared minus capital omega squared, and all this is squared. Due to the Pythagorean theorem, I have to take this squared here. Plus the imaginary part, and the imaginary part here is 2 beta capital omega squared. So that will be 4 beta squared capital omega squared. All this is square root. That's it. We have found the amplitude of forced oscillations as a function of capital omega which is the driving force frequency, or external force frequency. That's the main thing. That's the main purpose of our calculations. And what remains to be done, we have to analyze this function somehow. And in order to analyze, we will start from zero frequency. Imagine that the external force has zero frequency omega. It means that we are just exerting some force on this spring pendulum. What happens? It will be displaced and there will be no oscillations. The oscillation frequency is zero. So that will be just the amplitude of displacement. The amplitude of displacement, I will denote it as A0. That is when omega is zero. And that will be what? If this is zero and this is zero, I will have omega 0 squared and squared, that is to the power of 4 and square root. What remains is the omega to the power of 2 in the denominator. So it will be f0 divided by m omega 0 to the power of 2 after I take square root of omega to the power of 4. So from here I can, sorry? Omega 0 squared and squared to the power of 4, and we take square root. What remains is second power omega to the omega squared. That's it. Everything's correct. So from here we can find this quantity, which is f0 divided by m. That will be omega 0 squared amplitude at zero frequency. So the final amplitude, or not quite final, but some preliminary expression may be put as this f0 divided by m, what is found in denominator here, can be expressed as omega 0 squared amplitude at zero frequency divided by all this expression square root of, well, if we have square this round bracket squared, then it doesn't matter what order of terms is here. I would like to put it like capital omega squared minus omega 0 squared plus 4 beta squared capital omega squared. So what I've done, I eliminated this unknown term, which has some vague meaning. What is the amplitude of force? What is the mass? I don't know. So I have expressed it in the form of an own frequency of oscillations of oscillating system, and the amplitude, that is the displacement at zero frequency of driving force. Now I will divide all this expression by omega 0, and that will give me A0. If I divide by omega 0, both numerator and denominator, omega 0 will go under the square root as omega 0 to the fourth degree, and then I will put it here. It will be in this way. It will look in this way: capital omega squared by omega 0 squared minus 1 squared plus 4 beta squared, and what we have here, omega squared divided by omega 0 to the power of 4, right? And I will introduce a new variable, which will be f, for example, some some new variable which will be introduced as defined as capital omega squared divided by omega 0 squared. So this expression will become a at 0 frequency square root of f minus 1 squared plus 4 beta squared. That will be f divided by omega 0 squared. Well, my purpose is to draw a graph of this function and to investigate what will be the maximum, where will be the maximum of this function. Can I draw a graph of this function immediately? Yes, I can do it, even if I look at this expression. When omega, so I would like to draw a function of the amplitude of oscillations as a function of the driving force frequency, capital omega. So when capital omega is 0, the amplitude will be just a of 0. Some displacement, some deformation of the spring under the constant force when the driving frequency is 0. Some deformation of the spring under constant external force. Why is it constant? Because its frequency is 0. And then what happens then? If omega increases from 0, that will somehow change. And if omega is very large, if it's very high, then omega 0 can be neglected here. If capital omega is much larger than omega 0, it can be neglected here. And that will be omega, capital omega to the power of 4. That will be the main term here. It will be much larger than omega, capital omega to the power of 2. And so to the power of 4 will be the main term here. And so when I take the square root of it, I will get omega, capital omega squared in the denominator of this formula. So at very large omegas, that will be something like that, proportional to omega squared. So somewhere in between, there must be a peak at some external frequency, which I will call a resonant frequency. How can I find the resonant frequency if I have this formula? How can I find the maximum of this formula? I have to differentiate it with respect to omega and equate it to 0. But if this function is maximum, then its denominator is minimum. So I may differentiate the denominator. I don't have to differentiate the square root. I may differentiate just this expression with respect to f. So let's do it. F minus 1 squared plus 4 beta squared f divided by omega 0 squared. I will take a derivative with respect to f and equate it to 0. So if I take a derivative, I obtain 2 f minus 1 equal to, or no, plus 4 beta squared divided by omega 0 squared equal to 0. 2f, is that correct? Two f minus 1, yes, and here is just 4 beta squared omegas. Yes, that's correct. So I have to find f from here. That will be what? If oscillation system is has very small damping coefficient, if it's very small damping coefficient, then this actually can be neglected. That will be very small number, as that will be very small number, and so that will give me just f equal to 0, f equal to 1, and f, if you remember what is it, then you will obtain omega resonant will be practically equal to omega own omega. So we have found this omega resonant, which is practically omega 0. Unfortunately, that's the end of our lecture, and I was unable to tell you to discuss the half-width of this resonant curve. This is called a resonant curve, and there is a half-width of this resonant curve if you take the maximum amplitude at the resonance and another amplitude, which is a maximum divided by square root of 2. Then, if you use this formula and take into account that this amplitude is square root of 2 smaller than this one, then you can easily find the frequency range or the width of this resonance curve. Well, I hope you could read this simple derivation at home. This is not a complicated thing, because if you divide it by square root of 2, then this square root is equal to square root of 2, that is equal to 2, and from here it's very simple to find. It's not difficult to find the deviation of omega from the central resonance frequency. So that's let's finish at this point.